In chapter 4.1, we'll be going over exponential functions. So an exponential function is going to be in the form f of x. So a function with respect to x is going to equal b to the x. So the b we call a base. The b is a number, and then we have x as the variable in the exponent. So for example, something like f of x equals 2 to the x. So that's an exponential function. We have base 2 with the variable x in the exponent. And something else like g of x equals 10 to the x plus 1. So we have an expression with the variable in the exponent this time. This would be base 10. And h of x, for our next example, 1/2 to the x minus 1. So that is also an exponential function with base 1/2. So let's do some examples for evaluating these. So for the first one, we have f of x is 2 times 3 to the x, and we want to find f of 2. So we're just plugging this in here, so it's going to be f of 2 is going to be 2 times 3 squared, so plugging in that 2 makes it squared, and then you just have to make sure you don't mess up order of operations. We have to do the exponent first, so 3 squared, which is 9. So 2 times 9, so f of 2 equals 18. And for this next one, we have g of x equals negative 2 times 4 to the x, and we want to find g of 1/2. So we're going to plug in 1/2 into x, so negative 2 times 4 to the 1/2. So you have to remember that a 1/2 power is the square root. So the square root of 4 is 2. So this is negative 2 times 2. So that's going to give us negative 4. So g of 1/2 equals negative 4. So let's graph two examples of these, and we'll do it by plugging in x values and finding their y values so we can plot the ordered pair. So for the first one, we have f of x equals 2 to the x. So I'm going to use integers for x between negative 3 and positive 3. So I'm going to plug in these values into f of x here. So let's do f of negative 3. That's going to be 2 to the negative 3. So we have to remember how these negative exponents work. This is the same as 1 over 2 to the positive 3, which is 1 over 8. So that's going to give us a coordinate of negative 3 comma 1/8. For negative 2, plug in a negative 2. This is going to be 2 raised up to the negative 2, which is 1 over 2 to the positive 2, which is 1/4. So this gives us the coordinate negative 2 comma 1/4. If we plug in a negative 1, 2 to the negative 1 gives us 1 over 2 to the positive 1, or just 1 over 2. And if we plug in a 0, 2 to the 0 equals 1. So that's the coordinate 0 comma 1. If we plug in a 1, 2 to the first power equals 2, 2 to the second equals 4, and 2 to the third equals 8. So we're going to plot all of these points. So negative 3 comma 1/8 is going to be all the way down here. Negative 2 comma 1/4 about right here. Negative 1 1/2 right here. 0 comma 1, 1 comma 2, 2 comma 4, and then 3 comma 8. And then just connect these with a smooth curve. So it'll look something like that. So this is our function f of x. So that's what this form of exponential looks like. Let's do another one. So we have g of x equals 1/2 to the x. So let's plug in those same values for x. So I'm going to use the values negative 3 to 3, the integers between negative 3 and 3. So let's plug these in. So we have, for the first one, 1/2 to the negative 3. So 1/2 to the negative 3 is going to be 2 to the positive 3, which is 8. So you reciprocate, if it's a negative exponent, you reciprocate the base, and then you make the exponent positive. So that gives us the coordinate negative 3, 8. So plug in a negative 2. So 1/2 to the negative 2. That becomes 2 to the positive 2, which is 4. So negative 2, 4. If we plug in a negative 1, so, oops, that's going to be 1/2. 1/2 to the negative 1 gives us positive 2. So it's going to be 2 to the positive 1, so just 2. Plug in a 0, that's going to give us 1/2 to the 0, which is 1. Plug in a 1, 1/2 to the first is 1/2. Plug in a 2, 1/2 squared is 1/4. And then 1/2 to the third is 1/8. So I'm going to write all these down as coordinates. Negative 1, 2, 0, 1, 1, 1/2, 2, 1/4, and 3, 1/8. So plotting all of these coordinates down, we have negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1, 1/2, 2, 1/4, and 3, 1/8. So once again, connect all these with a smooth curve. And it'll look something like that, and that is our g of x. Okay, so you can see the difference here. The first one, 2 to the x, was exponentially increasing. 1/2 to the x was exponentially decreasing. So you can probably see the difference. The 1/2 to the x, it was a value between 0 and 1 for the base. 2 to the x was a value greater than 1. So that's what makes it increase for that one. So for 1/2 to the x, we also could have rewrote that as 2 to the negative x. Those are the same thing. So 2 to the negative x, comparing that with 2 to the positive x, it's a reflection over the y-axis. So if you negate the x values, it reflects it over the y-axis, which you can tell that these graphs are just the same thing, but they're reflections over the y-axis of each other. All right, so going over some of these properties for the exponential functions. So this is just looking at the exponential functions in the form b to the x. The domain is going to be all real numbers, so negative infinity to positive infinity, and the range is going to be from 0 to infinity. The y-intercept, when it's in this form, is always going to be 1. It's going to be y equals 1, so it's going to be the coordinate, the ordered pair 0, 1. So that's because if we plug in a 0 into the x, it's going to be b to the 0, which is equal to 1. And as we saw on the last page, it kind of breaks down into two different graphs. Either if the base is greater than 1, that means the function is increasing. So that means it would look something like this. So this is for b greater than 1. And we know it has a y-intercept of 1. And the larger the base, in this case, the larger the base is going to result in a steeper incline. The steeper the incline. So it's going to be increasing faster. So if the base is between 0 and 1, that's going to be decreasing. So that would look something like this. So we saw that on the last page also. So this would be for the base between 0 and 1. And for this one, the smaller the base, so the smaller the b value, the closer to 0, this is going to mean the steeper the decline. So exponential functions are one-to-one functions. So one-to-one functions, if you remember, means they pass what we call the horizontal line test, meaning anywhere we draw a horizontal line, it's going to intersect it at only 1 point, no more than 1 point. So if it passes the horizontal line test, that's what we call a one-to-one function. If it's a one-to-one function, that means it's going to have an inverse function, which we'll be getting to in 4.2, I believe. And there's actually a horizontal asymptote at y equals 0, which is the x-axis. So right here we have a horizontal asymptote at y equals 0. So it's going to asymptotically approach the x-axis. It's going to get closer and closer and closer to it, but it's never actually going to touch it. Okay, so we're going to do maybe just one example using transformations for exponential functions. So hopefully you kind of remember some of these transformations from at some other point if you've done them before this class. So we're going to be doing these transformations on f of x equals b to the x. So for a vertical shift, we know it's going to be a vertical shift if we're adding or subtracting a number, which I'm just calling c. So all these c's represent numbers. If we're adding it after the fact, that's going to be a vertical shift. So if we have b to the x plus c, that means we're shifting b to the x up c units. If we have b to the x minus c, that's going to be shifting it down c units. So that's for a vertical shift. For a horizontal shift is when it's done directly on the x. So you can see the plus or minus c is in the exponent. So if we have b raised up to the x plus c, that's going to be a shift to the left. So you have to remember horizontal is opposite of what you think. Plus means to the left. And then if we have b to the x minus c, that's going to be to the right. So we just move the graph to the right c units. For the next one, for reflections. So reflections are when we're essentially negating. So if the first one here, we have g of x equals negative b to the x. So we're negating the whole thing. We're negating the function values, which means we're negating the y values. When that happens, we reflect over the x-axis. If we have a negative x, so the next one has a b to the negative x, you negate the x values, that means you reflect over the y-axis. So it would be the graph of b to the x, but reflected over the y-axis. Next one, vertical stretch or shrink, g of x equals c times b to the x. So we're multiplying the c out front, which means we're multiplying all the function values by that number c. It breaks it down into two cases, just like every other one has two cases above. If c is greater than 1, that means it is a vertical stretch, meaning it's moving away from the x-axis. It's making all the function values larger away from the x-axis. If c is between 0 and 1, that's making them smaller, the function values, meaning it's a shrink, meaning it's the function, the graph is getting closer to the x-axis. And the last one here, horizontal stretch and shrink. So horizontal, once again, it's being done to the x. We have b to the c times x, so the x is being multiplied. And it's going to be the opposite of what you think, what we just did for the vertical. If c is greater than 1, this is going to be a horizontal shrink, meaning it's going to be getting closer to the y-axis, the graph. And then if c is between 0 and 1, that's going to be a horizontal stretch, meaning it's getting stretched away from the y-axis. So let's do an example of this. So we have f of x. We're going to use f of x equals 3 to the x to graph g of x, which is negative 3 to the x plus 1, and then plus 2. So we always need to start with what I call the basic function or the parent function. So in this case, the basic function is going to be what they gave us. It's going to be y equals 3 to the x. So we need to graph that. So graphing that, you can plug in some points if you want. So if you plug in, let's make a little table here. So I'm going to make this easy and only use 3 values. I'm going to plug in -1, 0, and 1. So we should know what it looks like by now. Y equals 3 to the x. It's exponentially increasing. If we plug in a -1, 3 to the -1 is 1/3. If we plug in a 0, 3 to the 0 is 1. If we plug in a 1, 3 to the first power is 3. So if we plot these points, that's going to be here, here, and here. That should be enough to let us know how it looks. It looks like this. So that's our basic function. So once we have this basic function graphed, what we're going to do is we're going to keep on applying these transformations one at a time until we get our end result. So I'm going to also just put in this horizontal asymptote because that can move, which we'll see in a little bit. So horizontal asymptote, y equals 0, right on the x-axis. Okay, so for the first transformation that you have to check is for the horizontal shift. So there is a horizontal shift here. The horizontal shift is the x plus 1. That means it's going to be to the left 1 unit. So we're going to move every single one of those coordinates we just plotted to the left, and then we're going to draw that curve back in. So it's going to look something like this. And you draw that back in, and we get that. So there's still a horizontal asymptote at y equals 0. Okay, so we just moved the whole thing to the left 1 unit, easy enough. So I'm going to just label this. This graph that we just drew is 3 to the x plus 1. So the next thing that we would have to check for would be stretching and shrinking. So just remember when looking back, the order that you do this does matter. First, you check if there's a horizontal shift. Then you check if there's any vertical or horizontal stretching or shrinking. Then you check if there's any reflection. And then you do vertical shift last. Okay, so it does matter. So for looking at this function here for g of x, we don't have a vertical or horizontal stretch or shrink. We don't have a number other than 1 or -1 being multiplied out front or being multiplied on the x, so we can skip it. The next step would be checking if there's a reflection. So there is a reflection here. We have this negative being multiplied out front. So the negative being multiplied out front means we're negating the y values, the function values, which means it is a reflection over the x-axis. So reflection over x-axis. So what we have to do is we go to the previous graph, so that's the one on the right, the horizontal shift. We're going to take all of those values and reflect them over the x-axis. So it's going to end up looking something like this. So essentially what this means is we're just negating the y values. X values stay the same, we negate the y values. So connect these. And it looks like that. Once again, we still have this horizontal asymptote at y equals 0. So now this graph is y equals -3 to the x plus 1. We only have one more thing on here. We have that +2 at the end. The +2 is a vertical shift, and it's going to be a vertical shift up 2 units. So that's going to be our final graph right here, which will be our final answer. So this is going to be vertical shift. And it's going to be a vertical shift up 2 units. So we go to the graph that we just did, and we move everything up 2 units. So it's going to be about here, here, and here. And we draw those in, so something like that. What you have to look out for, though, for this is that vertical shifts will move the horizontal asymptote. So this has a horizontal asymptote at y equals 2. So it moved it up 2 to y equals 2. So this is now our function g of x, which is negative 3 to the x plus 1 plus 2. Okay, so that's an example using transformations. So moving on to this next thing. So really, really important, these next few things here. The natural base e. So e is just a number. It's just a constant. Just like pi, we just use a letter to represent it. So e is going to be approximately 2.7182818 . So it may seem like there might be some repetition here. There actually is no repetition. It's going to go on forever, and it's never going to repeat itself. So what that means is that it is an irrational number. So for the properties of this number, just like pi, it is an irrational number. Goes on forever. Decimal version goes on forever. It doesn't repeat itself. The reason, not really the reason why we necessarily use it, but one of its properties is it shows up naturally. It shows up in many exponential functions. We use it for a lot of different reasons, though. So for one of them, something like population growth, which we'll actually see in a little bit, in a couple sections. So we'll see this in a population growth function. And the last thing, which is going to be a little bit of calculus concept, is limits, but it is really important. I'll kind of bring it back in a little bit. The limit as x goes to infinity, so I'll explain this a little better after I write it, of 1 plus 1 over x, all raised to the x, equals this constant e. So what that means, ignore the limit portion for a second. If you have the expression 1 plus 1 over x raised to the x, and you start plugging in numbers that are getting larger and larger, so plug in 100, plug in 1,000, plug in 1,000,000, plug in 10 trillion, that number that you get after you plug it in is going to approach 2.7182818, and so on. So that number is going to approach e as the x values get larger and larger, meaning as x goes to infinity. So that's actually, I believe that was the first definition for e. Now we have many different definitions for it. So I'll be coming back to that in a few pages, actually. Okay, so let's actually graph this. So I'm going to plug in numbers for x, -2, -1, 0, 1, and 2, and get out its y-coordinate and then graph it. So for -2, e raised up to the -2, this would be 1 over e squared, which is going to be about 0.14. So I rounded that a little bit. Plugging in a -1, e to the -1 is 1 over e to the +1, which is going to be about 0.37. And then e to the 0 is going to be 1. E to the first is just going to be e, which we know is about I'll put 2.72. And then for e squared, that'll be about 7.39. So writing down all of these coordinates, we have -2, 0.14, -1, 0.37. Notice that this also has a y-intercept of 1, and then 1.272, and 2, 7.39. So if you're looking in your calculator and your scientific calculator, the exponential for the natural base e should be, you have to click the second button and then it should be under the ln, the natural log, which we'll get to. And then you can raise it to a power and evaluate it. So -2, so I'm going to plot these points down and connect them. So you can see that it looks no different from like when we graphed f of x equals 2 to the x. So it should look similar to that because this is just about 2.718 to the x. So it just looks like an increasing exponential function. Okay, so we'll come back to that in a few pages. So switching gears just a little bit, moving on to simple interest. So simple interest is going to be money earned by initially investing some money. So the initial investment is going to be called the principal, and a percentage, which is the interest, is going to be added to the principal, making that initial investment grow. So taking a look here for the formula for calculating interest that was gained or lost. The total interest gained after t years, so t represents years, with an initial investment, p, which is the principal, and the percentage rate, r. You just have to remember to convert the percentage rate to a decimal. The formula is going to be I equals p times r times t. So it's a pretty easy formula. And if we want to calculate the total amount that you have after t years, so I is only the interest gained. So if you want to calculate the total amount, A, after t years, what you would want to do is you would say the total amount is going to be your initial investment plus any of the interest earned. So it's A equals P plus I. So what I'm going to do is I'm going to, instead of writing I, I'm going to write P times R times T, because we just said that that's what the interest equals after t years. What we can then do is we can factor out a P, and we'd be left with 1 plus RT. So the shortcut formula would be what's actually written, what's actually typed down here. It would be A equals P times 1 plus RT. So if you were at a bank and you invested some money, you gave them a principal, a down payment P, and then after T amount of years, you gain some interest on that, your total amount in your account would be your principal back plus that interest. So it'd be this total A value right here. So let's do an example with these. So let's say you would invest $1,000 in an account for 5 years at a simple interest rate of 6%. And we want to know how much interest will you have earned after 5 years. So we're looking for interest. So it's going to be I equals P times R times T. So we're given P, the initial investment, $1,000. We're given T, that's the 5 years. And we're given R, just remember you need it as a decimal. 6% as a decimal is 0.06. So you just have to move the decimal over 2 to the left. So this is essentially doing 6% of 1,000 5 different times. So plugging these in for the interest is going to be 1,000 times 0.06 times 5. So the interest gained here is going to be $300. Okay, so you invested $1,000 for 5 years at a simple interest rate of 6%. The interest that you gained from that money was $300. So now let's say we want to know what's the total amount you have in your account after these 5 years. So that's the interest that you got was $300. If we want to know the total amount, that's going to be A equals the principal times 1 plus RT. So remember, this is from the last page. So you can 100% do it this way, and you can plug in P, you can plug in R, you can plug in T. Or what you can do is say it's the same thing as the amount equals the principal plus the interest. So remember, those are the same thing from that last page. So all we have to do is say that's going to be $1,000 for the principal plus $300 for the interest gained. So that's going to be a total of $1,300. And that's going to be dollars. So that's going to be the total amount in your account. So you started off with $1,000. You invested $1,000 at a simple interest rate of 6% for 5 years. After that 5 years, you now had $1,300 in your account. Okay, so that's simple interest. The next thing is going to be a little bit more complicated. The next thing is compound interest. So the difference here is for compound interest is going to be interest compounded on the original investment, as well as any of the accumulated interest throughout those years. So the formula that we're using here is the total amount, which is going to be the initial amount invested plus all of the accumulated interest after t years, is going to be A equals P times 1 plus R over N, all raised to the N times T. So let me explain these variables real quick. So A, which we kind of already have, but I'll write it down anyway, is going to be the total amount. The total amount after t years. P, once again, is the principal. Which is the original investment. The R is going to be the interest rate or the percentage rate. Percentage rate compounded once per year. And once again, you have to make sure that that's in decimal form. I'll make a note of that. Decimal form, and then T is in years. And the one that we probably didn't know is going to be N. The N represents the number of compounding periods. The number of compounding periods per year. So this is essentially how many times per year the interest is calculated and added to the original investment. Okay, so the main difference here is simple interest. You have this set interest rate, which is saying, for example, if it was 6% per year, that's 6% of the original every year. For compounded interest, that's saying you're going to calculate an interest, and then you're going to have a new amount, and then you're going to calculate the next interest for the next compounding period based on that new amount, instead of just having that set interest like simple interest was. So going back to the number of compounding periods per year, there are several different kind of main types of compounding periods. The first one being semi-annually. So semi-annual compounding, that means there would be 2 compounding periods, semi meaning 2. So N would be 2. As soon as you see the word semi-annual, that means 2, twice per year. If you see quarterly, quarterly compounding means 4 times per year. So that would mean N equals 4. For monthly compounding, monthly compounding would be 12 times a year, so N equals 12. And for the last one that we'll worry about is daily compounding. For daily compounding, we could use N is 365. Okay, so let's do an example actually using all of these and see how they compare, how their total amounts compare after we're done calculating them. So let's say you invest $5,000 in an account for 4 years. At a percentage rate of 8%, we want to calculate the total amount of money in the account for each of these compounding periods. So for the first one, we have compounded annually. So if it's compounded annually, that means n equals 1. So I didn't write that one on the previous page because that one isn't used as often because it's kind of obvious and it simplifies a lot. So if it's compounded annually, that's once per year, so n equals 1. So we're going to be using our formula A. We know we're doing compounded interest, so A equals P times 1 plus R over N to the NT. So we need to plug everything in. So our P here is 5,000. T is going to be 4 years. The interest rate is going to be 0.08 as a decimal. So plugging all this in, we're going to get A equals 5,000 times 1 plus 0.08 over 1 raised up to the 1 times 4. I'm going to put parentheses so it doesn't look like 1.4. So when you're calculating this, what I recommend doing is doing the points. Well, you don't have to do it for this one, but I would divide the R divided by N, click enter. I would add the 1 to it in the parentheses, click enter, raise it up to the N times T, click enter, and then multiply that result by P to get your final answer, just so you don't mess up order of operations. So the total amount here is going to be $6,802.44. So you invested $5,000 in an account for 4 years at a percentage rate of 8%. And after those 4 years, the total account amount was $6,802. Okay, so for semi-annually, that means n equals 2. That's twice per year. So once again, same formula. We get A equals P times 1 plus R over N to the NT. So we plug in our values. That's 5,000 times 1 plus 0.08 over 2 raised up to the 2 times 4. So if we calculate that, that's actually going to give us 6,842.85, so in 85 cents. So you can see that it's a little bit more than the original one, than compounded annually. So let's see what happens again. Compounded quarterly. Quarterly means n equals 4. So that's going to be same formula once again. And when we plug everything in here, that's going to be 5,000 times 1 plus 0.08 over 4 raised up to the 4 times 4. So if we plug that in the calculator, that's going to be 6,863.93. So once again, you can probably see that this is getting a little bit larger, but it's getting a little bit larger at a slower rate. So second last one, compounded monthly. So same formula, plugging everything in once again, 5,000 times 1 plus 0.08 over 12. So this was for n equals 12. Raised up to the 12 times 4. This will end up giving you 6,878.33. Once again, it's a little bit more than the other ones. And now for the last one for daily. This one's going to be when we have 365 compounding periods. So on day 1, we would calculate the interest from the initial amount. Day 2, we would calculate the interest from the new amount, which was the principal plus the interest earned on day 1. On day 3, we would calculate the interest earned on the principal plus the interest earned on day 2, and so on. So that's just the definition of compounded once again. So for this one, plugging in the values, it's going to be 5,000 times 1 plus 0.08 over 365, raised up to the 365 times 4. So that's a huge exponent, right? 365 times 4. So normally you would think that that would super dominate that number and make it super large. But since in the parentheses we're dividing by 365, it's making that other number very, 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 very small. So when we add that other number to 1, it's not going to be a lot larger than 1. So even though the exponent's huge, the exponent's going to be on a number that's very close to 1. So it's only going to result in 1 point something. So this is actually going to result in 6,885 and 40 cents. Okay, so compare that with monthly, which is still on the screen here. Monthly was 6,878. This was 6,885, which is not that much more, which you probably would think that it would be a lot more because of the amount of compounding periods, 365 compared to 12, but it actually ends up not being that much more. So we could do semi-daily, that would be twice per day. We could do hourly, which would be 24 times per day. So we can keep on compounding more and more frequently. And you might think that the price would keep on increasing. You would be correct to think that. But you might think that you can get like an infinite amount. But you actually can't. There's actually a cutoff. And that brings us to continuous compounding, which will bring us back to our natural base E. So let's say we wanted to have our compounding periods be infinite, which means it's continuously compounding interest. What that would mean, essentially, there's a little bit more to it. Essentially, that would mean n would go to infinity. So the number of compounding periods would be an infinite amount throughout the year. Then the formula that we end up getting, the total amount, instead of the formula we were just using, is going to be A equals P times E to the RT. So E being the natural base. So since n is essentially infinity, we could not use the formula that we were just using because you can't plug in infinity. So that's where that limit comes into play. So if you want to know why, we know that the total amount for the compounded interest formula is what we just did. A equals P times 1 plus R over N to the NT. And like I just mentioned, we can't just plug in infinity for continuously compounding. So what we actually do is go back to that limit that I mentioned several pages ago. The limit as x goes to infinity of 1 plus 1 over x raised up to the x equals E. So you can kind of see, like I mentioned, there's a little bit more to it, but you can kind of see how the formula that I have written to the left here that we were just using is similar to that limit. So you can hopefully see how that formula we were using before turns into this one that we are using now. A equals P times E to the RT. So this actually ends up resulting in a little more than daily compounding. So let's do 2 examples so we can kind of compare these. So let's say you wish to invest $8,000 for 6 years. You have to choose between 2 accounts. One pays 7% interest per year, compounded monthly. And the second pays 6.85% per year, compounded continuously. And we want to know which account's going to result in the greatest amount of money after 6 years. So we're going to essentially do 2 problems. Let's do the first one as the 7% compounded monthly. So we'll do this one first. Okay, so if it's compounded monthly, we know that we're using this formula. A equals P times 1 plus R over N to the NT. Monthly means that n equals, right over here, monthly means that n equals 12 times per year. The 7% is 0.07 for the R value. And T for both of these problems, T is going to be 6 for 6 years, and the P is going to be 8,000. So let's plug all of those in here. So it's going to be A equals 8,000 times 1 plus 0.07 over 12, raised up to the 12 times 6. So like I mentioned with plugging these into the calculator, try to do it in one swoop. Don't try to round and then calculate the answers while you're rounding, because I will throw it off by a little bit. So if you plugged all of this in, you would get $12,160.84. So you started with 8,000. You invested for 6 years. You paid 7% interest per year, compounded monthly, and then you ended up with a little bit over $12,000. So let's see what happens for the other one. Let's see what happens if we invested at a rate of 6.85% compounded continuously. So as soon as you see continuously, that means you are using this formula, A equals P times E to the RT. So for this one, we obviously don't have an n here because n is essentially going to infinity, continuously compounding. The R is going to be 0.0685. The T is still 6, and the P is still 8,000. So we plug all of this in. It's going to be 8,000 times E to the 6 times 0.0685. You plug that in your calculator. Obviously, you have to use the button for E. And you're going to get $12,066.60. So if you want to know, the question was asking which account's going to result in the greatest amount of money. That's going to be the 7% compounded monthly. So it's barely more. It's less than $100 more, but it is still just a little bit more. Okay, so let's do, I believe this is the last one. Yep, let's do one more here. So let's do same type of question. You wish to invest $3,000 for 8 years. You have to choose between two accounts again. One pays 5% interest per year compounded daily. The second one also pays 5% per year, but it's compounded continuously. We want to know which account is going to result in the greatest amount of money after these 8 years. So before you even do this one, you should be thinking about which is going to be the answer, which is going to result in the greater amount of money. There is a shortcut way to do it, which I'll mention right after we do it. So for the 5% daily, we know that we need this formula, A equals P times 1 plus R over N to the NT. So daily means we have 365 compounding periods. We have R is 0.05 for the interest rate. T number of years is 8. The principal, down payment, the original investment is 3,000. So we have everything we need, so it's just plug and chug again. So 3,000 times 1 plus 0.05 over 365 raised up to the 365 times 8. This will end up giving us 4,475 and 35 cents. So when you're doing these problems, if the interest rate is close to each other, if it's, which they are in this case, they're actually equal, your values, your answers should be decently similar. If they're really far away from each other, you probably did something wrong. Okay, for the next one, we have 5% continuously. So 5% compounded continuously. So as soon as you see continuously, you should be thinking A equals P times E to the RT. And the R here is going to be 0.05 again. The T is 8, and the P is 3,000. So plugging all of these in, we get A equals 3,000 times E to the 0.05 times 8. And this will end up giving you 4,475 and 47 cents. So comparing these values, that was really close. They were both $4,475. Continuously compounding earned you an extra 12 cents. So hardly worth it, but it was a little bit more. Coming back to how I said you knew which one was going to be more before you even did any of the work, they were both 5%. Whenever it's the same percentage rate, whichever one has more compounding periods, that'll be the one that earns you the more money. So continuously compounding is obviously more compounding periods than daily because you're continuously compounding it. So we knew that one was going to be more. Not by a lot, apparently, but still more. Okay, so continuously compounding results in a greater amount of money in this case. All right, so that is it for section 4.1.